Hi, this is Mr. Mac. This is a concept video on sequences. I may do a couple of things a little bit out of order from the way your book has them, but basically it'll all be there. So we're talking about sequences. Now, first of all, a sequence really in your mind probably is an ordered list of numbers. An example of that might be 2, 5, 8, 11, 14, 17, ... Something like that. Now, it's a number of things that I would like you to know. First of all, there are different types of sequences. Two of the very main types that we're going to take a look at in this particular chapter are arithmetic and geometric. Now, it's important that you keep arithmetic and geometric sequences separate in your mind. The basic thing is, with an arithmetic sequence, you have a common or a constant that's being added every time to get the next term. The sequence that I showed you here is arithmetic because notice if you start with 2 and you add 3 to 2 you get 5, add 3 to 5 you get 8, add 3 to 8 you get 11, add 3 to 11 you get 14, add 3 to 14 you get 17, and so on and so forth like that. So the sequence that I showed you there is an arithmetic sequence. Now, geometric sequences are ones where there's a constant multiplied each time to get the next term. Okay. To get the next term. Okay, now I'll just say this: if I gave you two numbers and asked you to add them and you multiplied them, would you expect to get the right answer? Well, of course not. So if you're dealing with an arithmetic sequence and you treat it like a geometric sequence in any way, you're going to get the wrong answer. If you're dealing with a geometric sequence and you treat it like an arithmetic sequence, again, you're going to get the wrong answer. And if you have a sequence and you haven't determined which of these it is and you just start working with it, most likely you'll be doing things that are not correct. So please, 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 always while you're working on sequences, be aware of which type you're dealing with. Now, let's go back and I want to just grab a lot of this, group it together, and then we'll put it over here, kind of make it smaller in case we need to bring it back. But first of all, a couple of basic definitions or terms. What we're going to do is we're going to define a sequence. See, in other words, the definition of sequence is going to be a function with the domain restricted to the natural numbers. Now let's stop for just a minute and take a look at the sequence we have up here. Let's call this sequence A sub n. Okay. Now, if we were to say A sub n is equal to f of n, where f of n is equal to 3n minus 1, notice f of 1 is 3 times 1 minus 1, or 2. F of 2 is 3 times 2 minus 1, or 6. F of 3 is going to be 3 times 3 minus 1, or 8, and so on and so forth. So this function, and more precisely, this expression right here, will tell us what the numbers are in this ordered list when we put in a particular number. Now, the number we put in is the input, and what we're doing is we're restricting the domain, or the input numbers, to the natural numbers. So when we put 1 in, we get 2. Now we consider 2 to be the first term in the sequence. So a lot of times, instead of using f of 1, what we'll do is we'll say a sub 1. Now 2 is a term in the sequence. A sub 1 is an expression that represents the first term in the sequence. 5 would be a sub 2. Now we'd find that by putting 2 in the sequence, or just adding 3 to 5, to 2. A sub 3, dot, 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 and so on like that. And we read these symbols, a sub 1, a sub 2, a sub 3. The sub actually means subscript, but we don't say a subscript 1. We just say a sub 1. A sub 2, A sub 3. Sometimes we shorten it to A1, A2, A3, but that's probably being just a little bit too lazy. So let's get in the habit of calling it A sub 1, A sub 2, A sub 3. Now, if I said to you, what is A sub 5, you should know from that that I am saying, find the 5th term in the sequence. And you could put 5 into 3n minus 1 and get 14, or you could count 1, 2, 3, 4, 5. If you have the list already out, say it's 14, whatever. So we have, we have functions or sequences are functions with the domain restricted to the natural numbers. We have the ordinal numbers, the inputs, 1, 2, 3, and we use the term ordinal numbers for them because they tell us the order, or where that number is in the order of the terms. And then the output numbers are the terms of the sequence. Now, let's go to, or let's talk about arithmetic sequences in a little more detail here. Some of this is not contained in the first section of the chapter in the book. Some of it's contained in the second chapter, but this seems to be a good place to put it. Now, arithmetic sequences are defined by linear functions. So if you have an arithmetic sequence, then it is going to be defined by a linear function. Now, if you think about this, linear functions are f of x is equal to m times x plus b. Now, and let's think about this particular sequence that we have here, a sub n, 2, and then 5, and 8, and so on like that. Now, when we go from term 1 to term 2, that's kind of like the input number has increased by 1, the output number has increased by 3. So in every term, we're always going to be increasing the input number by 1 each time. So it turns out that m, this number right here, is the constant that we add each time. Now this is called the common difference. So in other words, if you have a sequence, let me just go ahead and grab that and bring it down here. So if you have a sequence and you want to know the function that describes this arithmetic sequence, you can say f of n is equal to, and then you're going to use n, and you're going to multiply n by something, and then you're going to add something. Now, what you're going to multiply n by is the common difference. Now, you then simply need to say, all right, if n were 1, I would get 3 so far, but I want a 2, so what do I have to adjust it by? Well, I have to adjust it by -1. So f of n is going to be 3n plus -1, or 3n minus 1. And anytime you have an arithmetic sequence, that's a way to find the function, and more accurately, the expression that generates the terms of that sequence. Now, many times, the algebra books actually come up with a formula for the nth term of an arithmetic sequence. This is a little different. I recommend that you know both of these and you use them as you see fit. But what they'll do is they'll say the nth term of an arithmetic sequence is equal to the first term plus n minus 1 times the common difference, where you use d to represent the common difference. And this is a formula worth remembering also. The nth term of an arithmetic sequence is the first term plus n minus 1 times the common difference. If you think about this for just a minute, notice in the sequence we had 2, and then 5, and then 8, and 11, and so on like that. Notice 2 was the first term. We had added 3 to it 0 times. Now, 5 was the second term of the sequence. We had added 3 to it 1 time. 8 was the third term of the sequence. We had added 3 to it 2 times. And the fourth term, we will have added 3 to it, see, plus 3, plus 3, plus 3, 3 times. So, in other words, for the nth term of a sequence, we're taking the first term, and we're adding the common difference n minus 1 times. The second term we add d once, the third term we add d twice, and so on like that. So that's a way to help remember this formula. A sub n is equal to a sub 1 plus n minus 1 times d. So you can use either just creating the expression of the function, knowing that it's a linear function to get an arithmetic sequence, or you can use this formula for the nth term. They actually do pretty much the same thing. It's a slightly different way of looking at it. Now, let's spend a little time with geometric sequences as well. And I'm just going to scroll on down here a little bit. Now, remember, again, geometric sequences are different from arithmetic sequences. A geometric sequence is one where you multiply each time by a constant to get the next term. Let's take a look at an example of a geometric sequence. Let's let a sub n be equal to the set 3, 6, 12, 24, 48, 96, ... Now, notice here, every time, once we have the first term, we're multiplying by 2 to get the next term. So, it turns out that by our definition again, a sequence is a function whose domain has been restricted to the natural numbers. It turns out that f of n is going to be equal to, now, what we do is we take the first term of the sequence, and then we multiply that by what we're multiplying each time. Now, that's called the common ratio. Common ratio. By the common ratio raised to the n minus 1 power. Geometric sequences are always generated by exponential functions. Now look at this one with me. If we put 1 in for n, f of 1 is 3 times 2 to the 0. 1 minus 1 is 0. 2 to the 0 is 1. 3 times 1 is 3. F of 2 would be 3 times 2 to the 1, which is 6. F of 3 would be 3 times 2, well, 3 times 2 to the, what did I say, f of 3? F of 3 would be 3 times 2 to the, 3 minus 1 was 2. 2 to the 2 is 4. 3 times 4 is 12. Notice, once again, what the exponent is doing is it's counting how many times we've multiplied the first term of the sequence by the common ratio. In other words, f of n is going to be the first term, a sub 1, times r, we use r for the common ratio, raised to the n minus 1 is the more general formula of this. And this is a formula that I expect you to know as well. Geometric sequences are described by exponential functions. If you have an exponential function and you restrict it to its domain to the natural numbers, you will get a geometric sequence. Now, the book is going to ask you to graph these functions. And so if you take a look at this function here, yeah, let's just clone this and bring it down a little bit. You might ask yourself, what am I being asked to graph? This is just a list of numbers. Well, actually, there is an order to this, and that would be the input. In other words, a sub 1, a sub 2, a sub 3, a sub 4, and so on like this. So we're expecting you to graph the ordered pairs 1, 3, 2, 6, 3, 12, 4, 24, and so on like that. Now also, we are not expecting that you would connect these. Now, you spent time in the last section graphing exponential functions. A long time ago, you graphed linear functions and so forth like that, and you would find points and then you'd connect them with a straight line or a smooth curve. You do not do that in this particular case because these terms are all that you get of a sequence. And if you connect them, your graph is claiming that the numbers, or the ordered pairs in between are also in the sequence, and they are not. So you would only plot these points. Now, probably the next thing that you're asking yourself is it possible to use the calculator to graph these? And the answer is yes. Let me just say once again, because here we go, it's been a little while since we've been using the calculator to graph. You may use the calculator to graph, but in the assignment, if the book says to graph it, I expect to see it on your paper. I expect it on graph paper. All right, now, getting back to work here. Let's go ahead and graph this sequence right here. Now, what we have is we have f of n is equal to 3 times 2 raised to the n minus 1. Now in the calculator probably we'll use x or something like that, but we've got to figure out some way to get it to just plot the dots rather than connect them. Now there are a number of ways to do this. The way I like best is what I'm going to show you here. Okay, so first of all, we're going to make use of the list feature of the calculator. And we have done scatter plots before. These will not be scatter plots as much as dot plots, but we'll use the same features of the calculator. So to start off, you press Stat. Now that gives you this window right here, and you go into the Edit mode, and what we're going to do is we're going to edit list 1 and list 2, and then we're going to plot that list, those lists as list 1 being the x's and list 2 being the y's. So what you can do is you can type 1, enter, 2, enter, 3, enter, 4, enter, 5, enter, 6, enter, 1, 2, 3, 4, 5, 6. That's what we've got 6 there before we got to the dot, dot, dots. and then type in your amounts here. 3, enter. 6, enter. 12, enter. 24, enter. 48, enter. 96, enter. Now, once again, if you're going to use the dot plot thing on the calculator, list 1 and list 2 has to have the same length, so that dotted line has to be in the same spot. If you've got more in one than the other, it's going to blow up. Also, your window is going to have to be such that it will contain all of these. Now, we need the 0.13 and we need the 0.696. So our x min needs to be less than 1, our x max needs to be greater than 6. Our y min needs to be less than 3, and our y max needs to be greater than 96. So we could go to Window, and let's let x min be 0, and x max can stay at 10. X scale 1 is good. Now, y min 0, y max 100, and let's make the y scale 10. Now, if you press graph, calculator's not going to do anything. It's just going to sit there and smile at you. What you have to do is you have to tell the calculator to plot the dots using list 1 as your x's and list 2 as your y's. Now you do that by pressing second y equals, and you get to the stat plot screen. Press enter on stat plot 1, and you have to turn it on. Now, guys, let me say again, once you've turned it on, it's going to stay on until you turn it off. So if you're using your calculator for something else, and you change the window so that these dots won't fit inside the window anymore, the calculator is going to say dim type mismatch. So if that happens, press your y equals button, go back and turn off plot 1. But right now, we're going to turn it on, and then, and you can choose, there's 3 different marks you can choose. Then you can press graph, and notice there is the graph of that particular sequence. Now, there's one other feature of the calculator that I would like to share with you, and this is really pretty cool feature. And so let's take a look at this one, second quit. Now, if you want, you can get a list of a lot of terms of the sequence by using the recursion feature of your calculator. Let's go back to this first sequence here. A sub n is 2, 5, 8, 11, 14, and so on like that. Now notice what we're doing on this sequence is we're adding 3 each time. And the first term is 2. So one of the ways to get the calculator to list these terms for you is to just start and press 2, the first term, and press enter. Notice what I did was I pressed the first term in the sequence, and then I pressed enter. Now, because of recursion, I'm going to say I want to add 3 each time. So now, don't press the 2 again, but just press plus, and then 3. Now, look at the screen. See what it said? It says ands plus 3. Ands is the calculator's memory for the last thing it did. Right now, since you press 2 and enter, 2 is in ands. So if you press ands plus 3, the calculator is going to give you 5. Here's the really cool thing. You know what's in ands now? Yep, 5. So if you just press enter again without touching anything else, it's going to do ands plus 3, which is 5 plus 3, and give you 8. And now guess what's in ands? Yes, 8. So if you press enter again, it's going to give you 11. But now, guess what? 11 is in ands, so if you press enter again, you're going to get 14. And you can just keep pressing enter, 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 and you can count the terms and get as many of these terms as you want by just doing that. Now, for geometric sequences, it works just as well. Look at this one. We have 3 as the first term, common ratio of 2. So if I press 3 and enter, the first term and enter, 3 is in the AND register. Now I'm going to press times 2. Look what the calculator did. It ANDs times 2. So when I press enter, it's going to give me 6. If I press enter again, it's going to give me 12. Enter again, it's going to give me 24, and then 48, and so on like that. And all you need to do, if for example we said give the 17th term. Now, no, well let's give the 10th term of this sequence. Press 3 and enter, and say to yourself 1. And then times 2, that's 2, 3, 4, 5, 6, 7, 8, 8, 9, 10. So the 10th term would be 1,536. That's a pretty cool way to do it, and the calculator will do that for you under the recursion feature. Now, that pretty much takes care of what you need for the first section of this chapter. So we're finished.